I've seen a lot of strange things in my day, but few moments have left me as awestruck as witnessing the impossible. Skyscrapers that seem to come alive. There's nothing quite like the sight of these massive towers, built to scrape the sky, suddenly swaying as if they're dancing to a rhythm only the earth can play. Picture yourself in a bustling metropolis, maybe Tokyo, maybe Los Angeles, where the skyline is a forest of glass and steel. Suddenly, the ground beneath your feet begins to tremble. It's not the rumble of a passing train or a heavy truck. This is deeper, more primal, the earth itself shifting. You look up, and the towers, those seemingly unmovable giants, are swaying, bending gracefully, almost as if they're reeds in a storm. It's a sight that's both terrifying and mesmerizing. The fear is real, but so is the wonder at what humans have built. Most of us expect these towers to be stiff, unyielding monuments to permanence and strength. But when they move, it's as if the rules of the world have changed. For a moment, it feels like the end of everything you know. And then, just as quickly as it began, the shaking fades. The city exhales. The towers return to their silent watch. The buildings settle, still standing tall as if nothing happened at all. This isn't just luck or chance. It's the result of decades of brilliant engineering and careful planning. The secret to their survival? To withstand an earthquake, a building can't simply resist. It must yield, flex, and move with the Earth's energy. Rigidity is the enemy of survival. History has shown us, structures that refuse to bend are the ones that shatter and fall. That's why engineers have equipped these towers with ingenious systems, shock absorbers, flexible joints, and deep foundations, so they can absorb the Earth's punches and keep standing. Watching a skyscraper sway in the sunlight, you realize the smartest builders don't fight nature. They work with it, learning its rhythms and adapting their creations. They took inspiration from trees, nature's own skyscrapers, which bend and flex in the wind, surviving storms that would snap a rigid trunk. So the next time you see a skyscraper dance during a quake, remember, it's not a sign of weakness, but of wisdom and resilience. Appreciate the quiet genius behind the scenes, a symphony of physics, design, and human ingenuity working together to keep us safe. These buildings aren't just tall, they're resilient, rooted deep, and designed to endure. Their true strength lies not in resisting movement, but in their remarkable ability to move and recover. That's the real marvel of the modern city, a landscape where science, art, and nature meet in every shimmering tower. The dance of the glass towers is more than survival. It's a testament to human creativity, courage, and the endless pursuit of harmony with the world around us. We think skyscrapers are immovable, like mountains, but that's a myth. If your home swayed, you'd panic. We equate strength with stillness, but in earthquake zones, rigidity is dangerous. If a building stands perfectly still while the ground moves, all that energy travels up, seeking weak points. The result? Collapse. So engineers flipped the script. They made skyscrapers flexible like fishing rods. Modern towers are designed to sway, sometimes several feet at the top. This controlled movement dissipates energy, turning violent jolts into manageable rocking. Think of standing on a bus. You bend your knees to absorb the shock. Skyscrapers do the same, flexing to survive. Engineers have taught steel giants to dance, not just stand. Flexibility saves lives. That's the real strength of a skyscraper. Earthquake resistance starts at the ground. The foundation is critical, but in quake zones, anchoring tightly isn't always best. Enter base isolation. Imagine the whole building on high-tech roller skates. Flexible pads or bearings separate the building from the shaking ground, letting it glide gently. Another method, deep piles or caissons, columns driven to bedrock, bypassing unstable soil. These piles flex with the earth, absorbing shock before it reaches the building. The choice depends on geology and building size, but the goal is the same: control how energy enters the structure. With base isolation or deep piles, skyscrapers can float above chaos or anchor to stability. It's a hidden solution beneath our feet. This is how towers survive the Earth's fury. The real battle is won underground. That's the foundation of resilience. Above the foundation, the building's skeleton is almost always steel. This strong, silvery metal forms the backbone of modern skyscrapers, rising story after story into the sky. Without it, our cities would look very different, lower, heavier, and far less daring in their designs. Steel's superpower? Ductility. It bends and stretches without breaking. Unlike other materials, steel can absorb huge amounts of energy, flexing under pressure and snapping back into shape. Concrete is strong but brittle. Steel frames are flexible heroes. When concrete cracks, steel simply flexes, making it the material of choice for earthquake-prone regions. The frame is a web of beams and columns connected to allow movement. This grid-like structure acts like a skeleton, supporting the building and letting it sway safely. Joints are engineered to flex, letting the whole structure absorb and distribute earthquake forces. Every bolt and plate is carefully designed to move just enough but never too much. When the ground moves, the steel frame bends, not breaks. This flexibility is what keeps buildings standing during violent tremors. Engineers use computer simulations to test designs, adding reinforcements where stress concentrates. These digital models help predict how a building will react in real earthquakes, long before construction begins. Diagonal braces create rigid triangles for extra support, but the overall frame stays flexible. This balance between strength and movement is key to earthquake resistance. The secret: yield, don't resist. By giving a little, steel saves the whole structure from catastrophic failure. Steel beams stretch, columns bend, but they return to shape after the quake. This memory-like quality is what makes steel so remarkable. This elasticity lets skyscrapers ride out earthquakes. Even in strong winds, the building can sway and flex, staying safe and sound. The real strength is hidden in the frame. It's the invisible guardian, quietly protecting everyone inside. It's resilience, not just height, that keeps towers standing tall after the shaking stops. The secret of the steel frame is what makes our cities possible. Flexible foundations and steel frames are great, but skyscrapers need brakes to control swaying. Enter dampers, the unsung heroes of modern buildings. Viscous dampers work like car shock absorbers, using thick fluid to turn motion into heat. Friction dampers use sliding plates to convert energy into heat, slowing the building's motion. These systems are simple, reliable, and always ready. Engineers use computer models to place dampers where they're most effective. Hundreds of dampers throughout a tower create a system that tames the sway. Movement isn't stopped, just controlled, making it safer for everyone inside. Dampers quietly dissipate violent energy, protecting the structure. They're the brakes that keep the dance safe. Without them, even flexible buildings could be damaged. Dampers are silent guardians. They make skyscraper survival possible. For the ultimate damper, look up at Taipei 101 in Taiwan. Once the world's tallest building, it faces typhoons and earthquakes. Its secret? A giant tuned mass damper, a massive steel sphere, 728 tons, hanging near the top. When the building sways, the pendulum swings opposite, canceling out motion. It's tuned to the building's frequency, providing the perfect counterpunch. Hydraulic cylinders act as shock absorbers for the pendulum. During a 2015 typhoon, the damper moved over 3 feet, protecting everyone inside. Other buildings use concrete blocks or water tanks as dampers, but the principle is the same. These systems are engineering marvels, giant dance partners for skyscrapers. Instead of just adding steel, engineers added movement. That's how Taipei 101 stands tall and safe. Earthquake engineering advances after every disaster. Each quake is a real-world test. Sometimes we fail, but we always learn. Engineers study collapsed and surviving buildings, searching for answers. The 1994 Northridge quake revealed weaknesses in steel frames, leading to better designs. The 1995 Kobe quake showed the dangers of soil liquefaction, prompting new foundation techniques. Lessons from disasters are written into building codes, which evolve after every major quake. Codes now demand not just strength, but flexibility and backup systems. Engineers use simulations and shaking table tests to improve designs before construction. It's a cycle: design, test, learn, improve. Each tragedy makes the next generation of buildings safer. The ghosts of fallen towers teach us to build smarter. Theories are one thing, but the real test comes when the ground shakes and skyscrapers are put to the ultimate challenge. It's in these moments that engineering is truly proven, not in blueprints, but in the buildings that remain standing after disaster strikes. Tokyo's towers swayed dramatically during the massive 2011 Tohoku quake, moving like blades of grass in the wind. But they didn't break. Their flexibility was by design, absorbing the shock and protecting thousands of lives. In Mexico City, the Torre Latinoamericana stood tall through the devastating 1985 quake. Built on deep piles that reached stable ground, it survived while many neighboring buildings crumbled, becoming a symbol of hope and resilience for the city. Los Angeles' U.S. Bank Tower swayed a staggering 18 inches during the 1994 Northridge quake. Yet, thanks to its advanced engineering, it stayed strong, protecting everyone inside and proving the value of modern design. These buildings aren't just structures, they're case studies in resilience, each one a testament to the power of innovation and preparation. Their survival confirms that flexible frames, deep foundations, and cutting-edge engineering really do work. Every detail from steel reinforcements to shock absorbers plays a crucial role in keeping these giants upright. Each surviving tower is a monument to smart design, human ingenuity, and a deep respect for the unpredictable power of nature. They show us that it's possible to build cities that don't just endure earthquakes but coexist with them, adapting and thriving in seismic zones. Every earthquake provides new data and valuable lessons, helping engineers refine their designs and making future buildings even safer for generations to come. These towers have taken the Earth's best punch, sometimes more than once, and are still standing, undaunted and unbroken. They're silent proof that knowledge, preparation, and relentless innovation truly save lives when disaster strikes. With the right design, we can build tall and tough. Our cities can reach for the sky without fear, knowing they're built to last. The next round is coming, and thanks to science and engineering, we're more ready than ever before. So what's the secret to skyscraper survival? Don't fight the shake, ride it. You can't stop earthquakes. The forces are too great. The goal is resilience, not resistance. Modern buildings are designed to move with the earth, not against it. Every element, from base isolators to steel frames to dampers, embraces flexibility. Skyscrapers survive because they yield, not because they stand rigid. It's humbling. We're not masters of the planet, just smart guests. The best we can do is understand the rules and build accordingly. A skyscraper's strength is in its ability to move, not its solidity. Next time you see a tower, think about the hidden systems inside. These buildings are monuments to wisdom, not just power. They ride the wave, and that's why they're still standing. Flexibility is survival. Next time you look up at a skyscraper, remember, it's not just tall, it's smart. Engineered to dance with the earth and still stand strong. If this amazed you even a little, give it a like and subscribe for more mind-blowing explanations like this.